In the previous class, we have discussed Euler's equation, and in today's class, so we'll discuss alternative forms of Euler's equations and examples of Euler's equation, right? So before that, one theorem is there, so we'll discuss the necessary condition for the functional I is equal to integration from x1 to x2 f of x, y, y dash dx to be an extremum is delta I is equal to 0. So what we know that here, we know that di by dh or d by dh of I is equal to integration from x1 to x2 dou f divided by dou y alpha x plus dou f divided by dou y dash alpha dash x dx. We know this. And delta I is equal to delta integration from x1 to x2 f of x, y, y dash dx. Since delta and integral are commutative with each other, we have delta I is equal to integration from x1 to x2 delta f of x, y, y dash dx. Using the expression for the variation of f being delta f in the RHS, we have delta I is equal to integration from x1 to x2 dou by dou I of f delta y plus dou by dou y dash of f delta y dash dx. But we know that delta y is equal to h into alpha of x and delta y dash is equal to h into alpha dash of x. So using these two results in this equation, so we will get here as integration from x1 to x2 dou by dou y of f into h alpha of x plus dou by dou y dash of f into h alpha dash of x dx. So from both these two terms, so h is common, take it outside. So take h common, integration from x1 to x2 dou by dou y of f alpha of x plus dou by dou y dash of f alpha dash of x dx. So delta I is equal to h is as it is. This is nothing but d by dh of this I or di by dh. But di by dh is equal to 0 when h is equal to 0, right? So this is the necessary condition for I to be extremum. So delta I is equal to, so this is 0 means you will get this as equal to 0. Delta I is equal to 0. So thus delta I is equal to 0 is also represents the necessary condition for the functional I to be an extremum. Now we'll discuss alternate forms of Euler's equation. So we have Euler's equation. So alternative forms of Euler's equations are as follows. First one, dou f by dou y minus dou square f divided by dou x dou y dash minus dou square f divided by dou y dash into y dash minus dou square dou y dash raised to 2 y double dash. This is equal to 0. And second one, d by dx of f minus y dash dou f by dou y dash. This is equal to dou f divided by dou x. And we have a particular cases. So in that f does not contain x and f does not contain y and f does not contain both y, x and y. So we need to discuss all the for you cases. Now first one, we have Euler's equation dou by dou y of f minus d by dx of dou by dou y dash of f. This is equal to 0. So this is our Euler's equation. So take this as a equation 1. Now first one, so A we need to prove first. So we know that dou f by dou y dash is a function of x, y, y dash. Because why this is a function of x y y dash? Because f is a function of x y y dash. Now let us take here z as a dou f by dou y dash or dou f by dou y dash as a z. So d by dx of dou f by dou y dash, so this is equal to, so we have taken this as a z. So d by dx of z is dz divided by dx. Right? Now, by using chain rule, so we'll write this as, sorry, by using total derivative rule, so we'll write this dz by dx as, so dz by dx is equal to dou by dou x of z dx divided by dx. So you'll get this as a 1 plus dou by dou y of z dy divided by dx plus dou by dou y dash of this z into dy dash divided by dx. So dy by dx is y dash and d by dx of y dash is y double dash. Now the above equation becomes dz divided by dx. This is equal to dou square f divided by dou x dou y dash, because we have taken z as a dou f divided by dou y dash, plus dou square f divided by dou y dash into y dash plus dou square f divided by dou y dash raised to 2 into y double dash, because we have taken z as dou f by dou y dash. Now you can put this in Euler's equation. So dou f by dou y minus dz by dx. dz by dx is nothing but what here? This one. So substitute. So we'll get dou f by dou y minus divided by dou x dou y dash minus dou square f divided by dou y dash into y dash minus dou square f divided by dou y dash raised to 2 into y double dash. This is equal to 0. Now move on to next one, b. So here again we are using total derivative rule. So we need to prove second one. So what is second one here? Second one, b is d by dx of f minus y dash dou f divided by dou y dash. This is equal to dou by dou x of f. We need to prove. So first find d by dx of f minus d by dx of y dash dou f divided by dou y dash, right? Find these two and take the difference, so you will get dou f by dou x, right? So first d by dx of f, right? So here again we are using total derivative rule to find this d f divided by dx. So this is equal to dou f divided by dou x into dx divided by dx. You will get this as a 1. So 1 into dou f divided by dou x is dou f divided by dou x plus dou f divided by dou y dy by dx plus dou f divided by dou y dash dy dash divided by dx, or d by dx of y dash. So d by dx of y dash will be y double dash. Dou f divided by dou y dash, this is as it is. Dy by dx is y dash and dou f by dou y is as it is, and this term is as it is, dou f by dou x. So df divided by dx, or d by dx of f, this is equal to dou by dou x of f plus dou by dou y of f into y dash plus dou by dou y dash of f into y double dash. Take this as a equation 2. Now d by dx of y dash dou f divided by dou y dash. So here y dash into d by dx of dou f dou y dash. So plus y double dash into dou f divided by dou y dash. Now applying u into v, right? This is u and this is v, right? uv rule, right? So keep this y dash as it is, differentiate this, plus keep this as it is, differentiate y dash. So differentiation of y dash will be y double dash. Take this as equation 3. Now 2 minus 3 gives, take the difference, 2 minus 3 gives df divided by dx minus d by dx of y dash dou f divided by dou y dash. This is equal to dou by dou x of f plus dou by dou y of f into y dash minus y dash into d by dx of dou f divided by dou y dash. So this dou f divided by dou x will be as it is. From these two terms, take y dash common. So inside will be dou f divided by dou y minus d by dx of dou f divided by dou y dash. This is nothing but Euler's theorem. So dou f divided by dou y minus d by dx of dou by dou y dash of f. This is nothing but Euler's theorem. So this is 0. So y dash into 0 is 0. So dou f divided by dou x plus 0 is dou f divided by dou x. So other side d by dx of f minus d by dx of y dash dou f divided by dou y dash is dou by dou x of f. So this is required second result or B. Next third one C. Suppose f does not contain x. This means f is independent of x. So f is independent of x means obviously dou by dou x of f is 0. Now substitute this 0 in result B. So we'll get here as d by dx of f minus y dash dou by dou y dash of f. This is equal to 0. We want here integrate this. So integration of d by dx of f minus y dash dou by dou y dash of f is f minus y dash dou f divided by dou y dash, and this is equal to k. So we need to add the constant because it is an indefinite integral. So where k is a constant. Now move on to fourth result or D. Suppose f does not contain y. F does not contain y means here f is independent of y. Obviously, dou f divided by dou y is 0. Hence, Euler's theorem becomes you do in place of dou f by dou y substitute 0. 0 minus d by dx of dou f divided by dou y dash. This is equal to 0. So minus d by dx of dou f divided by dou y dash. This is equal to 0. Again integrate integration of d by dx of dou f divided by dou y dash. This is equal to dou f divided by dou y dash. So this is equal to k. So dou f divided by dou y dash is equal to k, where k is a constant. Now suppose f does not contain both x and y. So obviously dou by dou x of f is equal to 0. Dou by dou y of this f is equal to 0. Differentiate these two partially with respect to y dash. So dou by dou y dash of dou f divided by dou x. This is equal to 0. Dou by dou y dash of dou f divided by dou y. This is equal to 0. So we'll get dou square f divided by dou x dou y dash is equal to 0, and dou square f divided by dou y dash, this is equal to 0. Using these two result along with this dou f by dou y is equal to 0, where in equation A or in result A. So we'll get here minus dou square f divided by dou y dash dou y dash raised to 2 into y double dash is equal to 0. So y double dash is equal to 0 provided this dou square f divided by dou y square dou y dash raised to 2 is not equal to 0. So this will be the required solution. Now before solving examples, so first, what is variational problem, right? So here we have to find extremal of the curve y is equal to y of x for the function I. So which passes through the points x1, y1 and x2, y2, and this must satisfy the following conditions. So condition 1 will be delta I is equal to 0. So what is I? I is integration from x1 to x2 f of x, y dash dx. This is equal to 0. So delta I means here delta integration from x1 to x2 f of x, y dash dx is equal to 0. And second condition, y of x1 is equal to y1, y of x2 is equal to y2. And condition 1 is called variational equation, and condition 2 is called end condition or boundary conditions. Now working procedure of this variational problem. So here what is given here? I is equal to integration from x1 to x2 f of x, y dash dx. So this will be given. So we have to solve here variational problem to find y, such that by taking this I as an extremum. So the necessary condition is that delta I is equal to 0. So this is equivalent to Euler's equation, dou f divided by dou y minus d by dx of dou f divided by dou y dash. This is equal to 0. Right. Now apply Euler's equation for the function f of x, y, y dash, right? So applying Euler's equation, so you will get an ordinary differential equation in y. Now solve that ordinary differential equation. So you will get a general solution. A general solution means here with arbitrary constants. And use the condition. If conditions are given, use the conditions. So you will get particular solution. Means, so by using condition, so we will find the arbitrary constants and substitute these arbitrary constants in general solution. So you will get a particular solution. So this will be the what here procedure. Now examples. First one, solve Euler's equation for the functional integration from x1 to x2 y dash plus x square y dash raised to 2 dx. So this is our given function, right? So here first f of x, y, y dash means a function involving these terms will be y dash plus x square y dash raised to 2, right? So observe this. So this is free from y dash plus x square y dash raised to 2 is free from y. So here dou f divided by dou y will be 0, right? Now Euler's equation is what? Dou f divided by dou y minus d by dx of dou f divided by dou y dash. This is equal to 0. Now this we don't have here y term, right? So f is independent of y. So this will be 0. Obviously dou f divided by dou y will be 0. So we'll get here as this as a 0. Now find dou f divided by dou y dash. Meaning of this, differentiate partially with respect to y dash. So differentiate this f partially with respect to y dash. So keep other variable x and y as a constant, right? So here y dash differentiation with respect to y dash means here 1 plus x square constant y dash raised to 2 differentiation with respect to y dash is 2y dash. 2y dash into x square is 2x square y dash. So dou f divided by dou y dash is 1 plus 2x square y dash. Now we have 0. So substitute these two in Euler's equation. 0 minus d by dx of 1 plus 2x square y dash is equal to 0. So our aim is to find here y. So first integrate this. So integration of d by dx of 1 plus 2x square y dash is equal to 0 is 1 plus 2x square y dash is equal to k1. We need to add the constant because it is an indefinite integral. Now we want y dash. Why we want y dash here? Because we need a y. So to find y, so first we need to find y dash. So 2x square y dash is equal to k1 minus 1 because you take this 1 from LHS to RHS. So k1 minus 1. So dy by dx or y dash, right? So y dash is equal to k1 minus 1 divided by 2x square. So this is a numerator, comes this side denominator. So k1 minus 1 divided by 2x square. So this is y dash or dy by dx. We need a y. So integrate again, right? So integration of dy by dx is y. Integration of dy by dx is y is equal to k1 minus 1 divided by 2. It is like a constant. Integration of 1 upon x square dx plus c2 because we have to add the constant because it is an indefinite integral. Now this is constant, right? Now integration of 1 upon x square. Integration of 1 upon x square is minus 1 by x. So multiply this minus 1 by x with this. So we'll get here as y is equal to c1 divided by x plus c2 because here minus 1 by x will be as it is. So multiply or we'll write this as 1 minus k1 divided by 2. So this as a C1. So minus C1, K1 minus 1 is there. So first you write minus 1 plus K1 and you take minus as common. So K1 minus K1 divided by 2. So this minus will be plus. So 1 minus K1 by 2. So I will take this as a constant and I'll denote this constant as a C1. Anyway, K1 is constant, 1 is constant, 2 is constant. I will take this whole thing as a constant, this as a C1. I will denote this whole thing as C1. So y is equal to, in place of this C1 and divided by x plus C2 will be as it is. So this is a required solution. Now move on to second example. Find the function y which makes the integration from x1 to x2 1 plus xy dash plus xy dash raised to 2 dx and extremum. So here what we have f of x y dash as, so we have f of x y dash as 1 plus x y dash plus x y dash raised to 2. Now Euler's equation you write down dou by dou I of f minus d by dx of dou by dou I dash of f. This is equal to 0, right? So again this equation is free from y. So independent of this y means here dou f by dou y. So this term will be 0. So substituting or taking this term as 0. So we'll get here as minus d by dx of dou f divided by dou y dash. This is equal to 0. So find dou f divided by dou y dash. So differentiate partially with respect to y dash. So partially, right? We are differentiating. So differentiation of constant 0 with respect to y dash means this is constant as it is y dash with respect to y dash is 1 and x constant as it is 2y dash raised to 2. So differentiation of this with respect to y dash is 2y dash. So you'll get here as x plus 2x y dash. So this is dou f by dou y dash. So dou f by dou y dash is x plus 2x y dash. So substituting, so 0 minus d by dx of x plus 2x y dash is equal to 0. We need y, so here first find y dash. So integrate this with respect to x. So we'll get here as integration of d by dx of x plus 2xy dash is x plus 2xy dash. This is equal to constant. We have to add the constant because it is an indefinite integral. So we want y dash. So for that 2xy dash is equal to k1 minus x. So we want y dash. So y dash is equal to k1 minus x divided by 2x. So first you simplify this before integration. So dy by dx, y dash means, so k1 by 2x minus x divided by 2x. X get cancels 1 by 2. So now you integrate. So integration of this dy by dx is y. This is equal to k1 by 2 constant outside. Integration of 1 by x dx minus 1 by 2 into 1 dx plus add constant c2. So k1 by 2 as it is, integration of 1 by x dx is log x minus 1 by 2 as it is, integration of 1 dx is x plus c2. So again, in any way it is a k1 is constant and this 2 is also constant. So k1 by 2, so I'll denote this constant as a c1. Again it is a constant. So c1 log x minus x by 2 plus c2. So we have taken here k1 by 2 as a c1. So this will be the required solution. Now move on to next example. Find the extremal of the functional integration from x1 to x2 y square plus y dash raised to 2 plus 2y e raised to x dx. We need to find the extremal of this functional. So let f of x, y dash is y square plus y dash raised to 2 plus 2y e raised to x. Now Euler's equation. So dou f by dou y minus d by dx of dou f by dou y dash. This is equal to 0. Now dou f by dou y, this is equal to 2y plus 2e raised to x. means differentiate this with respect to y partially. So differentiation of this y square with respect to y is 2y, and y dash is constant. Differentiation of constant is 0, plus 2 e raised to x is constant, and y with respect to y is 1. So we'll get dou f by dou y as 2y plus 2 e raised to x. Now dou f by dou y dash. So constant this is 0, and constant this is 0 because y constant 0, and y also constant, x also constant, 2 is also constant. So 2yx is a constant. So differentiation of this constant is 0. Left is this with respect to y dash. So y dash raised to 2 is there. You will get 2y dash. Now substitute this in Euler's equation. 2y plus 2e raised to x minus d by dx of 2y dash is equal to 0. So 2y plus 2e raised to x d by dx of y dash is y double dash. This constant is as it is equal to 0. Now 2 is common and take it outside. So 2y plus e raised to x minus y double dash is equal to 0. Now take this 2 to this side. 0 into something is 0. We'll get y plus e raised to x minus y double dash. This is equal to 0. Keep this y e raised to x is as it is. Take these two from left to right. So we'll get here as y double dash, because minus is there, comes this side, plus y double dash, plus y is there, comes this side, minus y is equal to e raised to x. So observe this. This is second order ordinary differential equation. Now we need to find y. So to find y, so solution contains two parts. So general solution. So this contains two parts: complementary function plus particular integral. So to find a complementary function, so we need a auxiliary equation. So using auxiliary equation, we will find the roots. So depending on roots, so we will write the complementary function of that equation. So first, y double dash means it is d square y minus y is equal to e raised to x. So this is equal to d square minus y is d square y minus y. So y is common, take it outside. So d square minus 1 into y is equal to e raised to x. So what is capital D? Capital D is d by dx. So d square will be d square divided by dx square. So auxiliary equation. What is auxiliary equation? F of d is equal to 0 is auxiliary equation. In place of d, substitute m. So yeah, auxiliary equation is m square minus 1 is equal to 0. So m square is equal to 1. So plus 1 minus 1 becomes here plus 1, right? Taking minus 1 from LHS to RHS. So 0 plus 1 is 1. So m square is equal to 1. So what is m? M is equal to plus or minus 1. So hence complementary function is equal to yc of x. So we have a different roots here. Roots are different. So depending on roots, we will write the complementary function. So complementary function, and it is denoted by yc of x. So this is equal to c1 e raised to x plus c2 e raised to minus x. So this is complementary function. Find particular integral. Particular integral is capital X divided by f of t. So this is a general form, right? So capital X is e raised to x divided by f of t is d square minus 1. So if suppose capital X is equal to e raised to ax form, what our rule says here? Our rule says put d is equal to a, where in f of t. So e raised to x is there. In place of a, we have a 1. So put d is equal to a. In place of a, 1. So put d is equal to 1 in f of t. So substitute e raised to x is as it is, divided by 1 square is 1, 1 minus 1. So this is equal to e raised to x divided by 1 minus 1 is 0. So whatever method we have applied, so our method fails. So alternate method we have to use. So particular integral is equal to x e raised to x divided by f dash d. So right. So here x e raised to x as it is, f dash d. F dash d is derivative of f of t. So d square minus 1, derivative of this is 2d. and 1 is 0. 2d minus 0 is 2d. X e raised to x divided by 2 as it is. Now in place of d, again you substitute 1 because a is 1. So put d is equal to a. So that is equal to 1 in f dash d. So substitute in place of d as a 1. So you will get x e raised to x divided by 2. So particular integral or yp of x is equal to x e raised to x divided by 2. Now we have general solution. Y of x is equal to yc of x plus yp of x. So y of x is equal to c1 e raised to x plus c2 e raised to minus x plus x e raised to x divided by 2. So this will be the required solution. So today we have discussed alternative forms of Today we have discussed alternative forms of Euler's equation and examples of this Euler's equation. So today I will stop here only. Thank you.